biodegradable as well as non-ecotoxic. So in order to develop bio-based food packaging materials, we need to find out a bioresource that can help to develop food packaging material to replace the petroleum-based food packaging material. Among bioresources, proteins from spent hen is one of the major resources. Spent hen are the old laying egg hens, that is the poultry byproducts. These old egg laying hens are not able to compete with the broiler meat because of the low yield, poor quality, and there are also a major concern with the spent hen because most of the poultry industry, they don't use it for the food purposes, they just dispose into the landfills. Because of that, these spent hens are economically infeasible, and also there is an extra cost from farm to the disposal sites, as well as it increases the operational cost. And most importantly, the disposal of these spent hen proteins are environmentally unfriendly and creates problem related to the air quality and groundwater contamination. We analyzed the spent hen proteins, and we found out that the spent hen proteins, the whole spent hen contains 1.6 to 1.8 kg of the total weight. And in this total weight, the protein contents are 17%. And in every year in Canada, around 32 million birds are disposed of. It means we can extract around 8 to 9 kilotons of proteins from these spent hens every year. So we can imagine how huge this bioresource that we can convert into food packaging materials. However, the proteins developed food packaging materials have poor mechanical strength, have lower thermostability, and they are very sensitive to the water contents. To overcome these issues, the introduction of the nanofillers is one of the viable options to improve these physiochemical properties. The main objective of my research project, the first objective was the extraction of proteins from the spent hen. Second objective is the conversion of these extracted proteins into the bio-nanocomposite films. And overall is the preparation of spent hen proteins into the films and then find out their suitability for the food packaging applications. Based on these objectives, the research question is, does the addition of nanoparticles into spent hen proteins can enhance the side chain on the surface and enhance their physiochemical properties? Based on this research question, the hypothesis for the research project is that nano-enforcement of the spent hen extracted proteins will modulate their physical and barrier properties by the addition of nanoparticles. Based on these, the following experiment design and methods were used. First of all, the proteins were extracted from the whole spent hen. Whole spent hen was mixed with the water with 1 to 4% ratio. And then the pH of this mixture was shifted to 12 by using sodium hydroxide. And then this was centrifuged. Furthermore, the 3 layers are formed, and then the pH was shifted to 5.75 at the isoelectric point to isolate the proteins. Furthermore, these extracted proteins were transformed into the food packaging films. For the conversion of these proteins into the food packaging materials, these are different plasticizers were used. Glycerol, sorbitol, ethylene glycol, 1,2-butyl-diol, polyethylene glycol with a percentage of 10, 20, 30, 40, and 50% to find out their best concentration that can help to develop the proteins-based food packaging materials. And then the water contents were used between 10 to 20%. Furthermore, the cross-linker agent chitosan was used with 1, 3, and 5%. At the end, the 3 different nanoparticles were tried to improve the physiochemical properties of these proteins. The first one is the bentonite, the second one is the glycidyl pause, and then the cellulose nanocrystals. These 3 nanoparticles were used with 3 different concentrations of 1, 3, and 5%. After the addition of all these contents into the proteins, the mixture was processed using Kerber press to develop the films using compression molding at a temperature between 120 to 130 degree. And these are the films that you obtained using bentonite, that is nanoclay, and cellulose nanocrystals. And the third one is the PAS-based, proteins-based films. After the synthesis of these films, these were characterized and the proteins purity was analyzed. The approximate analysis of the ground spent showed that the moisture content was around 67%, while the protein contents are 17% that I already discussed. And then the proteins extracted using this method, the recovery yield was around 74% and the percentage purity was 97%. After the successful extraction of these proteins, these are further characterized using different techniques. The first thing that we study is the stress and strain of the films. These are the films that develop from proteins without addition of any nanoparticles. And these are the films with nanoparticles. The first one is the bentonite, then PAS, and the cellulose nanocrystals. As we can see that the stress or the mechanical strength of the film was 2.43, which was increased up to 11.37 by the addition of the nanoparticle, that is bentonite. From this, we furthermore only characterize the films which have maximum tensile strength, that is bentonite, PAS, and cellulose, with 40% glycerol and bentonite 5%, glycerol 3%, and cellulose nanocrystal 5%. So we only characterize the materials with a maximum tensile strength. This is the stress strain curve of the films developed. A is basically the maximum tensile strength of the bentonite with the addition of bentonite that we obtained around 12 megapascal. And we can see that from the control how much increment have been obtained for mechanical strength by the addition of the nanoparticles. Furthermore, these films were characterized using FTIR. FTIR was used basically to see the structural changes after the addition of the nanoparticles into the protein's matrix. The first important peak that is observed at around 32 wave number belongs to the amide A region, or typically belongs to the OH. The second region is the amide 1 region, that is belongs to the carbonyl group of the amide. And the second region is called amide 2 region, that is belongs to the NH. And then third region is basically amide 3 region, that is related to the CN stretching and NH vibration of the amide groups. However, one of the most prominent peak that appeared in case of films containing nanoparticle, that is around 1700, that might be the presence of the ester linkage between nanoparticles and the films. Furthermore, amide 2 regions were expanded to see the changes in the amide 2 region. In the amide 2 region of the nanoparticles added proteins, we can see that the intensity in this region was increased. So that shows that the NH bond in this region have maximum number of hydrogen bonded as compared to the pure proteins. Further, second derivative of ATR FTIR was drawn of the proteins developed films, and we can see that the peak that is at 1660 wave number belongs to the 310 helix, and the next peak that is around 1653 belongs to the 1650 alpha helix, while the one extra peak that we can observe in case of bentonite developed films around 1637 that belongs to the beta sheets. And also these new types of interaction in case of bentonite, that might be the reason of maximum tensile strength in case of bentonite derived films. We also did XRD. XRD was performed to see the crystallinity patterns of the proteins after the addition of the nanoparticles. The first peak around 17.8 belongs to the alpha helix, and the second peak, that is around 19, a beta sheet structure. While in case of nanoparticles, we can see that there is a new peaks appeared. So it means there are new types of interaction have been produced between nanoparticles and the protein structure. And also there are the disappearance or the shifting of the peaks that shows the crystalline pattern of these proteins after the addition of nanoparticles have been changed, and new type of interactions have been developed that might be the increase of the physiochemical properties of the films. Then thermal stability of the developed proteins were measured using TGA. The first dump belongs to the loss of the water, and then the basic, the smaller groups degradation, and at the end is basically the degradation of the whole protein structure. However, by the addition of these nanoparticles, the overall stability of the proteins decreased because of the mixing of these nanoparticles with the proteins. They disturb the overall structure of the proteins. However, the proteins films containing bentonite has the highest stability among the developed films. The bottom graph shows the second derivative weight loss of the films. So we can see that in case of control, the maximum weight loss is around 160. However, in case of C and B, that the loss at the end has been decreased as compared to the control film. Furthermore, DSC, differential scanning calorimeter, was performed. The first loss around 116.52 degrees centigrade in case of control. However, that shifted towards the higher temperature in case of A, B, and C by the addition of the nanoparticles. And we can see that the A that contains bentonite nanoparticle containing films has the loss increase up to 166. That shows the maximum interaction has been developed in case of bentonite with the films. Furthermore, transmission electron microscopy was performed to see the internal structure changes after the addition of the nanoparticles. The A belongs to the protein films containing bentonite. In this case, we can see that either the nanoparticles are exfoliated or intercalated. However, in case of protein films containing cellulose nanocrystals, mostly aggregation can be seen. And in the third case, film containing pause, can see that there is introduction of the black spots that shows the presence of the silicon atoms in case of pause that has been introduced into the protein matrix. So among all, from this, we can conclude that the transmission electroscopy shows that in case of bentonite containing films, the distribution of the nanoparticles is better as compared to the other nanoparticles. That might be the reason of the maximum mechanical strength of the protein films by the addition of the bentonite as compared to the other two nanoparticles. Furthermore, dynamic mechanical analysis was performed to see the viscoelastic properties of the films. So in case of nanoparticle added films, we can see that there are three main peaks. However, in case of control, there is only two peaks, main peaks. So it means that by the addition of the nanoparticles, they undergo more thermal transitions. As a result, by the addition of the nanoparticles, the interaction between the nanoparticle and the proteins have been increased. And we can see that in case of nanoparticles, the area under the curve are also improved. It means they go more thermal transition and increase their interaction with the proteins that become the reason of the increase in the physiochemical properties of the protein-based films. Furthermore, water permeability analysis was performed. However, there is not significant increase in the water vapor permeability was seen. However, the water vapor permeability in case of A, that is belongs to the bentonite, is 2.18. However, in case of cellulose-derived films, the water vapor permeability was increased, little bit increased because of the presence of the hydroxyl group in the cellulose nanocrystals. From all these results, we concluded that the alkali added extraction is good method to recover the proteins from the spent hen. And among all plasticizers that we screened out, glycerol shows the best results. And 5% clay, that is bentonite, shows the highest mechanical strength. And these films are potentially biodegradable, while the films containing bentonite CNC cellulose nanocrystal have the lowest water vapor permeability. And in future, we want to investigate the biodegradability of these films and the leaching of plasticizer as well as nanoparticles from these protein-based films. And then the specific food will be tested for these developed films. Also, the industrial scale utilization will be determined by using other methods. And most importantly, the antimicrobial and the antioxidant study of these films will be done in future studies. At the end, I would like to acknowledge my supervisors, Dr. Amanullah and Dr. Jiping Bu, and all my lab fellows. And I also want to acknowledge the funding agencies and OCS, and as well as Canadian section OCS. Thank you so much.
So thank you, Mohammed, for this nice presentation. It's time now for the judges' feedback and questions.
Shall I go first again?
Yes, sure.
All right.
First.
Thank you for your interesting work and your presentation today. I have a few questions. The first one is, can you describe or provide us a bit more detail with how you prepared the whole, the spent hens before protein extraction? How did you receive the material, or in what state was the material in? And because you had mentioned it being ground, but between, you know, receiving it and getting it ready for protein extraction, how did you prepare your starting material?
So we took whole spent hen, dead whole spent hen from the farm, and then we ground it whole spent hen.
As is? I mean, no drying, just that, and just ground it?
First ground it, and then we dried it.
Oh, okay.
Yeah, we got the dead one from the farm, and then we ground it, and then we dried it. Yeah.
So everything.
Yeah, everything. Exactly.
All right.
Everything.
All right. My next question is, the films that you showed are colored.
Yeah.
And that could be a disadvantage in the final product.
Yeah.
Now, what imparts the color, and how do you envision taking care of that color issue if that is a disadvantage?
So for the color, we can use some of other nanoparticles such as titanium oxide, because that other nanoparticles can give the better color.
But would that not add to your final product cost though, if you still have to do that treatment?
Exactly. So the thing is, we will try to find out, because right now we are trying to figure out which food we have to package in this one, right? So we will try to find out that food where we don't need to consider the color, right? So if we be able to find that one, right, where the color impart in the package doesn't count for the food quality or the safety during packaging, then of course we will use that food. Otherwise, we may have to switch to another nanoparticles, but we have to consider other physiochemical properties too.
Okay. My next question is, you had mentioned that the alkali-aided extraction had an improved recovery, and that to me implied that perhaps you had compared it with other extraction techniques. Was that the case? And what other approaches did you attempt before settling on alkali-aided extraction?
So I used, because this one, I shift the pH to 11 or 12, right? So
right.
I did like in the extreme alkaline position, and then the extreme acidic conditions as well, between 2 to 3. Because the proteins can be solubilized extreme pH and the low pH in the acidic condition as well as in the basic condition. I did these two, as well as I also used different salts. But later on, I found out that the alkaline one was the best.
Okay. That's all I have for now. Thanks.
Okay, maybe I'll go then. Yeah, thanks, Muhammad. Very, very, very good work. Very interesting. My main question is, it's more of a fundamental nature. You have your protein, your protein isolates, which seems really fairly, very, very pure, 97% protein content. But do you actually know what types of proteins are in that extract? The different types of meat proteins?
Yeah, I did STS page, and the most of the proteins, the main concentration of the proteins are myosin proteins. Myosin, MY.
Myosin.
Yeah.
Okay.
Yeah.
Okay. So the fibers.
Yeah.
The fibrous proteins.
Exactly, myofibril. Yeah.
Okay. All right. And then lastly, one other very important part of biodegradable films like this is water and air permeability. Actually, if you're going to use it for packaging of foods, do you have any information on their water or air permeability?
Yeah, water permeability. I did water permeability, but there was not significant improvement in the water permeability of these films.
What about water? What about air? Sorry, like oxygen exchange.
Yeah, I think the two other main parameters I have to measure yet: oxygen and carbon dioxide as well. I haven't done these two parameters.
Yeah. Okay. Yeah, they'll be very, very important to know.
Exactly. Yeah.
Very important parameters to know
Yeah.
to be able to have some confidence in your product.
Exactly. Yeah.
Yeah, but overall, very, very good work. Thank you.
Hello, Mohammed. Very impressive work. I have some questions. So, yes, okay. So you mentioned, I think among your 3 to 4 samples, you all used glycerol, and you have one of your conclusions was about glycerol was a good plasticizer, for the system. So that sounds like you also tried other materials rather than glycerol. Did you mention that? Maybe I missed that. So what other things you have tried?
Yeah, I used 3 or 4 other plasticizers to just screen out which plasticizer working best in case of my proteins. I used sorbitol, I used ethylene glycol, and 2 others. So almost 4 different plasticizers are used.
And based on what characteristics you think glycerol works better than others?
So, the main purpose of the plasticizers is to increase the plasticization effect within the protein so the nanoparticles can interact, right? So in case of like whatever plasticizer are used, among those, in case of glycerol, it has symmetrical structure. So we concluded that because of that symmetrical structure in case of glycerol, that has better interaction with the proteins as compared to the other plasticizers.
Due to structure. All right. So the okay, you use XRD, look at the crystallinity of your system. So okay, so what's the conclusion for that? Okay, what type of crystallinity you get for you find into what type of sample, and that crystallinity, what type of crystallinity is so important for the water permeability, for example, or the barrier effect?
The study that I have done, in my case, there is not significant, not much improvement in case of water permeability. So from that, although we have after when we perform the XRD after these addition, we have new crystallinity peak. We just imagine that the new type of interaction has been obtained in case of nanoparticle.
Yeah. Do you have some hypothesis? Do you have some hypothesis that what type of crystallinity that you could expect as a better barrier property?
So, in my hypothesis, I just imagine that by the addition of nanoparticles that I seen in FTIR, there might be a new bond, that is extra linkage. So we just imagine that the new type of interactions can be produced. We are not looking into how the crystallinity will affect, but we just determine that the new crystallinity peaks are appeared, or either the crystallinity peaks are a new crystallinity appeared, or new that disappeared, or there are more separation between alpha sheets and beta sheet structures.
Okay, thank you.
But I think, of course, after the addition of nanoparticles, there might be a possibility of improved water permeability, but we haven't observed in our case.
Okay, thank you. And in your ingredient, one of your ingredients, in the recipe is a very interesting material, chitosan. So you use a chitosan, I think, for all of the materials, right?
Yeah.
So because chitosan itself can form a sort of a packaging film, how do you compare? What do you think if you, okay, let's say you don't have any protein into the recipe and you just make a chitosan film, how does that compare?
I would say the chitosan will give the better films with good mechanical strength as compared to the pure proteins.
Okay.
Yeah.
Okay. Well, if I may, one last question is: you showed the tangential delta, right? That's the tangential delta. You use that to indicate the mechanical strength. So, did you do some sort of amplitude sweep as well?
Sorry?
How did you get the tangential delta?
Oh, okay. So
time sweep?
Yeah, we performed dynamic mechanical analysis.
Using what instrument?
It's called DMA, dynamic mechanical analyzer. Yeah.
Okay, so you mentioned, I think one of your conclusions, you mentioned about the mechanical strength. So that mechanical strength is based on the tangential delta, right?
No, it's based on the stress and strain curve that is basically measured using the tensile testing analyzer.
Okay, okay.
Yeah.
Okay, okay, thank you.
Thank you. Okay, that's great. I don't think we have questions from the audience. I just have one question for you, Mohammed.
Yeah.
I see that you are using, of course, proteins from spent hen are biodegradable, but how about the safety of those added nanoparticles? Do you consider that?
Yeah, so nanoparticles in case of bentonite, that is nanoclay, that is FDA approved. They said we can use in storing and shipping of the food, and as well as CNC. But the third nanoparticle POS have not been recognized yet.
Okay. Okay, so thank you. I think this will end this presentation. Thank you, Mohammed. Thank you. Okay, so thank you. And so our last and fourth finalist today, it's Wen Hao Tsai. He's a graduate student also from University of Alberta, Canada, and will be presented today on the fabrication of strong heat-induced protein gels by combining soluble pea protein aggregates and carrageenan. So good luck, Wen Hao, and the screen is yours.
Okay. Hello, everyone. My name is Wen Hao Cai. I'm the PhD student in Dr. Chen's lab, and in this presentation, I will introduce the soluble pea protein aggregates from to form strong gels in the presence of κ-carrageenan. Field pea is one of the major legume worldwide with global annual production of approximate around 30 million metric tons. Field pea has attracted attention as a source of plant proteins from scientists and industries because of its high protein content, which is approximate 23%. And it has also has affordable price and good sustainability, so it has a large potential for the applications. And pea proteins contain two major types of proteins, albumins, and which is around 10% to 20%, and globulins, which is 70% to 80%. And the latter and the globulin can be further divided into legumin and visilin or convisilin. Which is also known as 7S. Legumin is a hexametric protein with a molecular mass between 300 and to 400 kDalton. The heterogeneity of the visilin originates from three subunit fragments, and convisilin has distinct amino acid profile from legumin and visilin with sulfur-containing amino acid and high charge N-terminal extension. Pea protein products has been reported to exhibit many comparable functional properties to homologous soybean protein products. However, many studies indicated that pea globulins possess a lower gelling capacity compared to soy globulins. A higher minimum concentrations was required for pea legumin to form gels, and it has been noted that heat-induced gels of pea protein were weaker than soy protein gels. Such difference can be partially ascribed to the lower amount of cysteine in pea protein that prevent it from forming disulfide bonds to stabilize the gel networks. So some new technologies are required to improve the gelling property of pea protein. to widen its food applications, such as plant-based binding ingredients in meat analogs formulation. Complexing with polysaccharides has been applied to modulate the microstructure and the mechanical property of protein-based gel systems. In previous research, both animal proteins such as whey protein and gelatin and plant proteins such as soy oat and chlorella proteins were complex with polysaccharides to achieve improved gelling properties. Using negative charged polysaccharides as examples, when pH is larger than protein isoelectric point, repulsion exists between protein and the polysaccharides when they are both negatively charged. Phase separate network can be formed with one network rich in protein and the other rich in polysaccharide caused by the incompatibility between these two polymers due to the repulsive force and the varying affinity towards the solvent. The increased apparent protein concentration as the result of protein exclusion from the space occupied by the polysaccharide promoted protein interaction to develop a stronger gel network. In the previous work, P-protein complex with polysaccharide like gum aerobic and alginate have been investigated and with the purpose to improve the protein emulsifying property and to form coadjuvation for microcapsule development. However, the research efforts to improve P-protein gelling property by complexing with polysaccharides is still limited. Thus, new modification strategy is required to achieve improved P-protein gel along or in complexation with polysaccharides. Protein aggregation is a biology phenomenon in which intrinsically disordered protein or misfolded protein aggregates. Often, normally, heat-induced aggregation of proteins is found to be irreversible, and the aggregates persist at room temperature. Heat-induced soluble protein aggregates are obtained by heating protein above the denaturation temperature to induce its unfolding and the reassociation when the protein solution is at a level below the minimal gelling concentration. In the denaturation and the aggregation process, many covalent and non-covalent interactions are involved. As for the Lingyun globular protein non-covalent interaction, including some like hydrophobic interactions and hydrogen bondings, they can dominate the association of the monomers to form soluble aggregates, and disulfur bonds are minimal bonds are minimal because of the lack of cysteine in the protein chain. Using protein aggregates as a pretexturization approach has been applied to increase the texture of diary protein-based matrices. Gels formed from the aggregates may possess improved strength due to the reinforcing effect of aggregate fillers. Also, the heating can expose the active groups on the aggregate surface to improve their interactions with each other to strengthen the gel networks. In such systems, the aggregate structure, size, charge, morphology, and active group directly determine the gel mechanical properties. Despite potential, gels prepared from P-protein aggregates have been seldom investigated. So in my research, I will investigate the gelling property of such kind of protein aggregates. In my research, heat-induced pea protein aggregates were prepared by incubating the pea protein solutions at 90-degree neutral condition for different times, like for like half an hour, 2 hour, and 16 hour, to observe the morphology of pea protein aggregates transmission by TM imaging. In Figure A, in Figure A, no intense aggregation was observed for untreated pea protein, as shown in Figure B and C. Soluble aggregates prepared by half an hour and 2 hour heating treatment appeared as a non-spherical particle with size of 50 to 100 nanometer, and 2 hours aggregates showed a slightly larger size. Previous research suggests that thermal treatments unfolded pea protein molecular to expose the hidden active groups, which then interact with each other to form aggregates. And the elongation of the pea protein aggregates was observed with prolonged heating time and longer strips with the length of 100 to 115 nanometer were formed after 16 hours of heating treatment. Heat-induced pea protein aggregates were prepared, and here shows the average size of untreated pea protein isolates and the soluble pea protein aggregates. The trend of the increase by heating treatment time, and all of the pea protein aggregates had larger size than native pea protein aggregates, size than native pea protein, and so it can also correspond with the TM results. The surface hydrophobicity of pea protein aggregates was also tested. The untreated pea protein exhibited lowest surface hydrophobicity because the hydrophobic groups were buried in the interior of the globular protein structure. The surface hydrophobicity increased almost 3 times when the pea protein was converted to aggregates by heating at neutral pH for half an hour. This was attributed to the protein unfolding during heating to expose the hydrophobic groups. Although the exposed surface hydrophobic group formed from hydrophobic interactions that played an important role to contribute to the protein aggregation. A significant amount of hydrophobic patches will still remain at aggregate surface. The surface hydrophobicity of the protein aggregates decreased to a certain extent when the heating process was prolonged to the 16 hours because the elongation of the aggregates to form strands consumed some hydrophobic patches at the aggregate surface. In this work, heat-induced soluble pre-protein aggregates were obtained prior to the addition of k-carrageenan, so that negatively charged k-carrageenan would not interfere with the unfolding and the aggregation of the pea protein. Then low concentration of the 0.5% k-carrageenan was dispersed in pea protein aggregate suspension, and it significantly improved the pea protein gel mechanical properties. In addition, this relatively low k-carrageenan content would not significantly decrease the protein content in the gel formulation, as protein claim is favorable for industrial applications. This also avoids gummy texture brought by polysaccharides in the final product. Mixture was then incubated in 95 degrees for half an hour. After the heat treatment, the mixture was cooled in an ice bath to form the gels. And to investigate the mechanical property of the pea protein aggregate gels, the instrument was used to test their properties. And the mechanical property of hydrogels prepared with untreated pea protein and soluble pea protein aggregates with κ-carrageenan was studied, and the results are shown in this figure. And based on previous research, based on our previous research, no gels were formed from untreated pea protein isolate solution or pea protein aggregates alone by heating at 95 degrees at neutral pH, because the protein concentration of 7.5% applied in this research was lower than the minimum gelling concentration of pea proteins. Our research work demonstrated that pea protein could form a gel at the protein concentration of 15% or higher when heated at 95 degrees for half an hour. As for carrageenan, the formed gels were too soft to be self-standing due to the low κ-carrageenan concentration of 0.5% applied in this work. Previous work also reported the formation of very weak gels by κ-carrageenan, like 1%, without the addition of cations. However, the addition of some κ-carrageenan, like 0.5% to untreated pea protein solution or pea protein aggregate suspension led to the formation of gels with good mechanical property. And in this figure, it displays the compressive strain curve of the complex pea protein carrageenan gels. Heating a mixture of untreated pea protein and κ-carrageenan at 95 degrees for half an hour lead to the gel with compressive strength of around 8 kPa, and the gel was broken at the compressed strain of around 42%. The formation of the good gels by combining a small amount of κ-carrageenan with untreated pea protein could be attributed to the formation of the phase separation gels. The incompatibility between pea protein and the κ-carrageenan was increased due to the heat-induced pea protein unfolding. This led to the increased apparent protein concentration when it was excluded from the space occupied by the polysaccharide. So promoted protein interaction to develop a strong gel network. Interestingly, the gel strength of the gel made by pea protein aggregates heated for half an hour, and the κ-carrageenan was almost doubled to achieve a compressive strength of 14 kPa, and the compressive strain was increased to around 57% before fracture of the gel. This indicated that using aggregates instead of untreated protein could significantly improve the pea protein gel mechanical properties, make them much stronger and elastic. The further increased gel mechanical property by using pea protein aggregates could be partially attributed to the significantly increased surface hydrophobicity on protein aggregate surface, rendering them more active building blocks to form hydrophobic interactions to reinforce the gel networks. Reduce surface charge on protein aggregates compared to the untreated protein might also contribute to strong gel formation, because the reduced repulsion could facilitate the development of attributed force among aggregates. Actually, no significant difference was observed for the gel mechanical property when they were prepared from 0.5 or 2 hours aggregates. However, the gel compressive strength was decreased to 6 kPa when the gel was prepared from 16 hours aggregates at the building blocks with κ-carrageenan. This result suggests that elongated pea protein strand aggregates might be less active for gel formation when compared to the shorter P protein aggregates particle, possibly attributed to the reduced surface hydrophobicity. The gel microstructure showed well cross-linked network in SEM imaging, likely due to the presence of copper-carrageenan that could form a polymer-like network based on associated double helix. Such pre-network could provide a sort of scaffold for more uniform growth of P protein aggregates into densely cross-linked gel network. It was noticed that a more uniform network with a smaller pore size was observed for the gel prepared from the half-an-hour aggregate sample with copper-carrageenan when compared to the gel formed from the P protein isolate of 16 hours aggregate sample. In conclusion, strong P protein gels were formed from P protein aggregates with small amount of carrageenan. The compressive strength could even reach 40 kPa. Above gel was achieved at the low protein concentration. Protein concentration for gelling was also 7.5%. And this research has provided a new method to develop strong P protein gels for food applications. Because nowadays, novel products are designed based on the growing preference of consumers for natural and healthy foods. And P protein aggregates derived ingredients show excellent potential to be well adopted by consumers. The utilization of P protein gels to produce food products of different textures could potentially contribute to the growth of the food and agriculture industries. Thank you, everyone. And any questions?
Thank you, Wenhao, for the nice presentation. And I think it's time now for the judges' feedback and questions.
Yeah.
Okay, last one. I might as well go first all the way. Thank you, Wenhao, for your work and for your presentation today. I have several questions. My first one is, did you prepare your own P protein isolate, or did you use a commercial sample?
We just extract the P protein isolate from the P protein concentrate got from the some companies, supported by some companies.
Like, what was the purity of your material then?
Yeah, like the P protein concentrate is like 55%, while the P protein isolate I extracted is higher than 90% of the protein concentration.
Okay. What was your reason for using kappa-carrageenan?
Because I tried several polysaccharides like aerobic, like pectin, sensing, and many other polysaccharides, including carrageenan, and find kappa-carrageenan has the best effect to increase the gelling property of the P protein.
What was your replication for your analysis? I mean, how many times did you run your tests? I mean, and your experimental replication?
Yeah, I think it has at least 3 times for the replication for every testing.
Okay. All right, that's all I have for now.
Thank you.
Thank
Thank you for
you.
the question.
I go second.
Hello.
Thank you, Wen Hao, for your presentation and your work. It's very impressive. I have a few questions and a comment as well. Let's go with questions first. So your surface hydrophobicity, right? So the longest treated sample had a relatively lower surface hydrophobicity. I think you explained a little bit why. Can you elaborate a little bit more why this longest heat treated sample had a relatively lower surface hydrophobicity?
Because during the heating process, the unfolding of the pea protein will make some hydrophobic groups be exposed to the surface, like outside of the like the surface of the protein, and at this stage, the protein aggregates form at the like half an hour or 2 hours. They didn't form a very large protein aggregates compared to the original native pea protein, and so the protein hydrophobic patches on the surface, it will not be consumed a lot. While during the longer heating time, like increase the heating time to 16 hours, these surface hydrophobic patches will be consumed to be used for the aggregation, like from the long strip of the aggregates showing the TM I present in the slides, and it will consume some hydrophobic patch to form the larger aggregates, like the 16 hours one.
Okay, so more like a secondary aggregation formed in the longer term of heat treatment. Okay, that makes sense. I remember in the title of this work you had, I think part of the title you mentioned like water soluble aggregates. Do you have that term in your title? Water soluble aggregates?
Yeah, I have that term because the protein solubility is because I just choose the water soluble part of the protein to conduct this kind of experiment to make sure the protein content in this gels to be uniform.
Okay, so that sounds like you did heat treatment, 5% of protein, and then you form aggregates, and then did you do centrifugation to get rid of the insoluble part?
No, I just prepared pea protein aggregates. I just do the centrifugation before prepare the pea protein aggregates.
Yeah, okay, that's understandable. But then how do you justify it is a water soluble aggregate?
Because if I just use centrifugation, the protein will not be precipitated in the bottom of the tubes. So I think it's soluble. Yeah.
You did
just testing
that
yeah,
and then you did a centrifugation.
Just testing their solubility, whether they are soluble in water.
And they are 100% of soluble?
The 100%.
What was your particle size?
The particle size is around 100. Like if the 0.5 an hour and 2 hours heat treatment, the particle size is around 100 nanometer, while the heating time was increased to the 16 hours. The size was increased to the 150 nanometer.
So that's Z average, right? That's not the okay. Then that leads to another question. So you at the beginning, your beginning material was the soluble fraction, right, of the pea protein. Therefore, do you know the composition of that soluble fraction? Did you do SDS page to look at the, because in your original P protein, you have some P protein has a high quaternary structure, and those ones are not soluble, which means you exclude a certain, population or types of the protein at the beginning.
Yes. Actually, I didn't do the SDS page. I just picked the soluble part of the P protein, and
I think it may be worthwhile to look at the the composition of the soluble fraction.
That's right.
Better understand what's going on in terms of the aggregation, right?
Yeah.
Okay. Last question is about the gelation mechanism. So you mentioned about you mentioned about you tried different polysaccharides, and the copper-carrageenan give you a good gel. So is this gel, hydrogel, is a protein mediated gel or simply polysaccharide mediated gel with just the protein dispersed into the gel? What's the feature of the gel?
Because the carrageenan I use in this system is really low concentration, I think it's protein mediated gel.
Then what's the mechanism of this protein gel?
Because the protein in this system, the pH is neutral pH, and is larger than the isoelectric point of the P protein, and so I think the P protein has a negative charge, while the copper-carrageenan also has a negative charge at pH 7. So I think they have some repulsion, like electrostatic repulsion, during this system. So it can be the phase separation network.
Yeah, so that's exactly, I don't understand how they could form a homogeneous gel.
Because in this system, the P protein and the carrageenan can be light in like in two kind of region. One is rich in P protein, while another is rich in copper-carrageenan, and they have their own networks, and the copper-carrageenan is like a triple helix, and it can be like a filler to reinforce this kind of gel, while the P protein aggregates can also form its own building blocks, and the main interaction formed by this kind of building blocks is the hydrophobic interaction and the hydrogen bonding. So I think this kind of two networks can reinforce this kind of hydrogel to have a stronger mechanical property.
Okay, yeah, thank you.
Okay, very briefly, I know we are running out of time. Thanks again, very interesting presentation. I just want to ask you, I could see from your data, I didn't see, the gelling properties of the proteins without carrageenan. Did you carry out their gelling properties without addition of carrageenan for comparison?
You mean without the carrageenan, the gelling property of the P protein? Yeah, we conducted this experiment in the previous research, and we find that even at high concentration, like 50% of the P protein aggregates, it cannot form a gel. If at 95 degree, maybe it requires a higher temperature to make them further unfolding or further denaturation to form a gel. So I think in this environment, the gelling is not feasible.
Okay. Yeah, okay, maybe you should just mention that. Yep. All right. Thank you very much.
Thank you.
Okay, thank you all. I think we have got one question from the audience. The attendee said, thank you very much. And what do you think about perspective to use protein gels in cosmetics?
Sorry.
So the question is about your perspective to use these protein gels in cosmetics.
In
Cosmetics, like for cosmetic products, like I don't know, like creams for for skin or things like that, I guess. Okay, so.
Oh, you mean the cosmetics? Oh, I think I at the beginning I meaning I think a lot about this kind of hydrogel to be applied to food products, but as for the cosmetics, maybe if they have the testing their emulsifying property, maybe they can apply to cosmetic. Maybe I can test it later. I'm not sure about this kind of about cosmetics.
Okay, thank you, Wenhao. So I think this ends the presentation and the question session.
Okay. Thank you, everyone.
Thank you. Okay, so thank you. The judges' scores have been tallied, and now it's time to announce our winners. Just to remind you that the first place winner receives a 200 cash prize, and recognition certificate, and a complimentary ticket to the PCP division dinner during the 2022 AOCS annual meetings and Expo in Atlanta. And our second place winner receives a 100 cash prize, recognition certificate, and the complimentary dinner ticket. So the runner-up is Yifu Chu. That's the second place. And the winner for this competition is Raliat Abioye. So congratulations to both of you, and thank you all to your participation. And I'm